Okay, good morning, students. So today I shall be starting with a new topic that is coming under the heading anterior aesthetic restorations. That is the resin-based composite restoration. The material aspect I shall be dealing with here in this chapter. And as I told earlier, composites are actually resin-based restoration that are setting via polymerization reaction that can be either that is an to be more precise, it is an addition polymerization reaction that can be powered by either, of course, that means that we need free radicals that is powered by either a chemical activator or a light activator. And as I told earlier, they are resin-based restorations that are they can be used for, they are aesthetic restorations, can be used for anterior as well as posterior teeth. And here in this image, you can see a fracture of the incisors that are involved in the Ellis class 2 fracture. You can see that it is involved in the enamel and the dentin. And you can see that the composite restoration, that is actually they are available in a paste-like consistency. Usually they are available either in the compules or they are available as a single paste system, and the composites can actually be contoured according to the anatomy of the tooth. And once you apply the curing lamp, then it converts from the paste-like consistency to a hard consistency via the addition polymerization reaction when the carbon-carbon double bonds get converted into single bonds. And thus, you can see the final completed and finished end restoration. Okay, and they adhere to the tooth via micro mechanical bonding. To the enamel, it is bonding via resin tags, the resin micro tags and macro tags, and to the dentin, it is actually bonding via the resin dentin interdiffusion zone, that is the hybrid layer. Okay, so they are to summarize, it is basically a resin based restoration that is setting via addition polymerization reaction involving free radicals, and it is an aesthetic restoration that is used for anterior restorations as well as posterior restorations, and also it adheres to the tooth via micro mechanical bonding. Okay, so now before moving on to the material aspect, first when I just referred your past previous year university question papers, then I saw that actually most of the time the long essay question, whenever composites are actually asked as the long essay question, the definition of composite is usually asked as the part of the essay question, long essay question. So you can see that generally a composite, it is not specified as a dental composite. This definition is given in your Anusavis Phillips Science of Dental Materials. Composite is a solid formed between two or more distinct phases. Okay, so when I am teaching about the definition about the composition of dental composites, you will see that basically there is a resin matrix. Okay, resin matrix, that is the resin component in which we find that organic or inorganic filler particles are actually dispersed. So you can see that there is a phase 1 and phase 2, isn't it? One is the resin matrix and other is the inorganic filler particles, and they can also be organic filler particles or there can be fibers also. Okay, so here we find that it is a solid that is actually mainly formed from two or more distinct phases. Okay, there are two or more distinct phases, that is filler particles that are actually dispersed in a polymer matrix that have been combined to produce properties that are superior or intermediate to those of the individual constituents. So when you are combining these two or more distinct phases, that is when you are combining the resin matrix and the filler particles, the final properties that you are getting is actually either intermediate to that of the resin matrix and the filler particles or superior to that of the resin matrix and the filler particles. Okay, and when coming to the dental composite, that is specifically, so this is actually generally for any composite material. So when you are asked about define dental composite, then you have to define it as a highly cross-linked polymeric materials. So that is basically denotes the resin matrix. Okay, highly cross-linked polymeric materials that are reinforced, highly cross-linked polymeric materials that are reinforced by dispersion of filler particles, which includes amorphous silica, glass, crystalline mineral, or organic resin filler particles or short fibers that are bonded to a matrix by a coupling agent. So here you can see that it is a, when I am explaining this definition, you find that there is a resin matrix. That is what they are denoting by highly cross-linked polymeric material, isn't it? And there are many types of filler particles. You can see there are crystalline filler particles like crystalline mineral, or you have amorphous silica, glass particles, or resin filler particles, or even fibers. Okay. Now they are also mentioning in the definition that these filler particles are actually not lying free in the resin matrix. They are bonded to the resin matrix via bonding agent, a silane based coupling agent. Okay. So that is the definition of dental composites. Okay. And here you can see the resin matrix in which the filler particles are dispersed. And to be more precise, you can see that each filler particle is bonded to the resin matrix actually via an interface that is actually composed of a coupling agent. Okay. And okay. So now moving on to the composition of dental composites. Okay. So when we are moving on to the composition of dental composites, the major components are actually the first three components. That is the resin matrix, the filler particles, and the coupling agent. So they are the major components. And then there is also an activator initiator system to that actually so as I told earlier, it is a addition polymerization reaction. Therefore, we need free radicals. So the initiator is the source of free radicals, and the activator is needed to activate the initiator to produce the free radical. And then there is an inhibitor to control the rate of the chemical reaction, and also optical modifiers that determine the color as well as the translucency. Okay. And so first we can actually start with the resin matrix. Okay, so whenever when I went through your previous year question papers, the composition of the dental composite is actually a repeated university question. It is the most simple question that you can get from this chapter. Okay, so the resin matrix is actually the chemically active component. That is the component of composite resin that gets involved in the chemical reaction. Okay, that gets involved in the chemical reaction or the polymerization reaction, the component that undergoes polymerization reaction. That is why it is actually called as the chemically active component of composite, is undergoes addition polymerization, and that results in the conversion of carbon-carbon double bonds of the monomer to the single bond in polymer. Okay, so basically we have the carbon-carbon double bond in the monomer, and when it undergoes addition polymerization reaction, then it actually gets converted into carbon-carbon single bonds in the polymer. So initially, when it is in the monomer state, we find that it is a plastic mass. Okay, so the ability to convert from a plastic mass into a rigid solid on polymerization, that allows it to be used as a restoration of the tooth. So in the initial slides, I had shown you images where that initially it is in a plastic state, when it is in the monomer state, where it can be molded according to the anatomy or the contour of the tooth. And once it polymerizes, then we find that it gets converted into a hard state. Okay, now the resin matrix in most dental composites is actually based on a blend of aromatic and or aliphatic dimethacrylate monomers. Okay, so that means that the monomer that used is actually either contains straight chain hydrocarbons or it is cyclic hydrocarbons. Either it is a combination, or it will be either it will be straight chain or cyclic compounds. Okay, and here we find that these monomers are actually containing two methacrylate groups. Okay, so once more I am repeating, it is a combination of straight chain hydrocarbons and cyclic hydrocarbons. That is why it is denoted as aromatic and or aliphatic. And not only that, we are having two methacrylate groups. So both of these methacrylate groups will contain carbon-carbon double bonds that will be converted to carbon-carbon single bonds during polymerization. That can result in a very strong, highly cross-linked matrix. Okay. And these monomers, the example of these monomers are actually bis-GMA and UDMA, urethane dimethacrylate. Okay. So, as I told earlier, they form a highly cross-linked, strong, rigid, and durable polymer structures. And this matrix actually forms a continuous phase. Okay, phase in which we find that the fillers are actually dispersed, the inorganic or the organic fillers. Most commonly used monomer for both anterior and posterior composites actually bis-GMA. Okay, bis-GMA, and bis-GMA, the full form is actually bisphenol A It is derived from the reaction, chemical reaction of bisphenol A and glycidyl methacrylate. Okay, bis GMA. It is a dimethacrylate monomer, and it is actually called as Bowen's resin after the name of its inventor R.L. Bowen in the year 1962. Okay, 1962. That is actually Bowen's resin, and then so here you can see that actually there is a bisphenol A. There is a bisphenol A and two molecules of glycidyl methacrylate. Okay, one molecule of bisphenol A and two molecules of glycidyl methacrylate that is actually resulting in this bis GMA. Okay, so you can see that there are two methacrylate groups containing carbon-carbon double bonds, and here you can see that this monomer is a combination of straight chain as well as cyclic hydrocarbons, isn't it? So bis GMA, and you can see like when you compare a complex molecule like bis GMA to a very small molecule like methyl methacrylate, you can see how a smaller molecule in size as well as in molecular weight also it is actually much smaller than compared to methyl methacrylate when compared to that of bis GMA, and I will be explaining the advantage of this. What advantages that a large molecule like bis GMA possesses over a small molecule like methyl methacrylate. Okay, so as I told earlier, we find that actually it has a very high molecular weight. Okay, a very high molecular weight of 8 lakh centipoise and also volume when compared to methyl methacrylate. And as you know that actually, um, when larger molecules like bis GMA and UDMA undergo addition polymerization, the amount of polymerization shrinkage will be less. Okay, so as you know that when the addition polymerization occurs, then we find that there is a decrease in distance between the monomer particles. There is a decrease in distance between the monomer particles, and when that is before the addition polymerization, the force of attraction between the monomer particles is the van der Waals force or the secondary force. So when this actually gets converted to a covalent bond, then we find that there is a decrease in distance. Now this decrease in distance is actually in the range of angstroms, that is 10 raised to minus 10, when two monomers are combining. But when many number of monomers, n number of monomers are combining to form a polymer, then we find that actually this decrease in distance between the monomers result in a reduction of volume, and this reduction in volume will be less if the monomers are actually very large. Okay, so the polymerization shrinkage value for methyl methacrylate resins, is actually 22 volume percent, whereas for bis GMA based volume resins only 7.5%. And adding fillers and also the polymerization shrinkage actually also depends upon the volume of resin that is entering the polymerization reaction. Therefore, we find that when they are combined with inorganic fillers, then the polymerization shrinkage is actually again reduced to 2 to 3 volume percentage. And as I told you here, there are actually two methacrylate groups instead of one methacrylate group, and use of dimethacrylates also results in extensive cross-linking that consequently enhances the resistance to degradation by solvents and also improves the properties. Okay, so two methacrylate groups means that there is more extensive cross-linking, and therefore we find that enhances the mechanical properties and also more resistance to dissolution by the oral fluids, and they are used as restoration. Okay. Now, like the bis DMA, we actually also have a UDMA or urethane dimethacrylate and also TEC-DMA, that is triethylene glycol dimethacrylate. Now, UDMA replaces the bisphenol A backbone with a linear isocyanate group. The structure of like bis DMA and UDMA are actually almost similar, and like you can see in this slide. Okay, so you can see that actually the structure in UDMA also we find that there are actually it is also a large complex molecule, and at the two ends you can see the two methacrylate groups also. Okay, and the bisphenol A is actually mainly replaced. The backbone is replaced actually by a linear isocyanate group. Okay, and however we find that actually this I told you that actually these composite resins are actually in a paste-like consistency. Therefore, they are actually easy to manipulate and they can be molded according to the contour or the shape of the tooth. So that is, they can be manipulated. They are easy to manipulate. But we find that bis DMA and UDMA, you can see that the molecules are so large that as a result, we find that the composite resin will become very viscous and they will be difficult to blend and manipulate with the tooth structure. So we need to decrease the viscosity. And for that, we will actually mix this BIS-DMA and UDMA with a low molecular weight, highly fluid monomer. Okay, so it is necessary to, so as a result, we find that actually we are actually mixing this BIS-DMA as well as UDMA with a low molecular weight monomer. Okay, so the low molecular weight monomer is actually also called as the diluent monomer because it actually decreases the viscosity. Okay, diluent monomer, low molecular weight, highly fluid monomer. Okay, highly fluid monomer. So that is actually the example is actually triethylene glycol dimethacrylate. Okay, so you can see that when compared to BIS-DMA and UDMA, you can see that the TEC-DMA molecule is actually very much smaller. Okay, so that is that. And then, okay, so the molecular weight, I told you that the molecular weight of BIS-DMA was 8 lakh centipoise, and here it is only TEC-DMA is only 5 to 30 centipoise. So to blend with and to dilute the viscous components, okay, and to attain a resin paste sufficiently fluid for clinical manipulation. So these diluent monomers decrease the viscosity, make the manipulation easier. Okay, so you can see that a blend of 75% BIS-DMA and 25% TEC-DMA has a viscosity of 4,300 centipoise, but yeah, as we take a 50-50 ratio, then we find that it is the viscosity, there is a drastic decrease in the viscosity, 200 centipoise. Now, as I told earlier, the addition of TEC-DMA, of course, decreases the viscosity and makes the manipulation easier, but at the same time, we find that actually these molecules are smaller. So the polymerization shrinkage actually also increases when you introduce more TEC-DMA into the mix. Okay, and so now I am actually moving on to the second major component, that is actually the filler particles. Okay, so I told you that actually in this resin matrix, we are actually having the second phase is actually dispersed. They are actually called as the filler particles, and these filler particles are bonded to the resin matrix via coupling agent. Okay, so various transparent mineral particles. Okay, they can be mineral particles that can be crystalline as well as amorphous in nature. Okay, transparent mineral fillers. So as to give the aesthetic appearance to the restoration. Transparent mineral fillers that are bonded to the matrix are employed to strengthen and reinforce the composite as well as to reduce the polymerization, shrinkage, and thermal expansion. There are many functions like they enhance the mechanical properties, reduce the polymerization, shrinkage, water absorption, and also make the coefficient of thermal expansion compatible between the restoration and the tooth structure so that the interfacial stresses are actually reduced. Okay. And generally between the filler loading, it will be either be described in weight percentage or volume percentage. Either it is 30 to 70% volume or 50 to 85% by weight. Okay, so the most common filler that is used is actually quartz or silicon dioxide has been used extensively as early versions of dental composites. Okay, so filler particle that is extensively used is actually the crystalline form of silica, that is actually quartz. Okay, and now the advantage of quartz is actually it is mechanically much superior. It's very hard and it is chemically inert, but it is actually also causes wearing away of the opposing tooth or the tooth with which it actually comes in contact. It is very hard and acting as an abrasive to opposing teeth and restorations, and it is also very difficult to grind, and also it is very difficult to reduce the size of these filler particles. Okay, into very fine particles, difficult to grind, and it is also difficult to polish these restorations. And so we find that even though they were hard and chemically inert, then we find that the amorphous variant of silica was actually introduced that has the same composition and refractive index, but at the same time we find that it is actually not as hard, thus reducing the abrasiveness of the composite on the adjacent tooth and restoration and improving the polishability. They can be easily polished. Okay. Now the third filler particle that was actually introduced was actually the glass particles. So the glass particles that they are actually mainly two types of glass particles that is given in your Phillips Science of Dental Materials, that is hard glass or borosilicate glass, and also soft glass that is based on aluminum silicate or lithium aluminum silicate. Now addition of the lithium as well as aluminum ions to the silica tetrahedra actually makes the glass easier to crush and generate small particles. Okay, that's soft glass. Lithium aluminum silicate, the another synonym is actually beta eucryptite. Okay, that has a negative coefficient of thermal expansion. Okay, that will be asked for your Viva point of view also. At the same time, glass particles that are actually having heavy metal atoms that are having a higher atomic weight, they can absorb more X-rays and provide more radio opacity. Ytterbium fluoride, barium, strontium, zirconium, and zinc glasses which impart radio opacity because of their heavy metal atoms. Okay. And the most commonly used glass filler is actually barium glass. Okay, now even though the glass fillers are actually containing metals of high atomic number and provide radio opacity, like quartz, we find that they are not chemically inert. Okay, they are actually slowly leached and they dissolve and weakened in acidic liquids. Okay, when we are actually, especially the beverages, acidic beverages we are consuming, or the acidic foods we are consuming, or when acidic fluoride medications like acidulated phosphate fluoride are applied. Citrus juices and high pH solutions and other oral fluids and caries protective agents are actually like acidulated phosphate fluoride solution or gels are actually applied. So glass fill composites will gradually become more and more susceptible to, and the resistance to abrasion is actually also okay. They are not mechanically as strong as quartz particles, and they are actually more prone to abrasive wear, and hence they will have a shorter functional lifetime when compared to that of silica reinforced resins. Okay, and now coming to the function of fillers. So the first function of fillers is actually reinforcement, enhancement of the physical and mechanical properties that will actually enhance the clinical performance. That it increases the compressive strength, tensile strength, modulus of elasticity, toughness. Okay, and as the volume fraction of filler, as the volume percentage as well as the weight percentage, the filler loading is actually improved. We find that the abrasion resistance and fracture resistance is actually also raised, approaching, that is, it mimics that of normal tooth tissue, that is enamel and dentin. Okay. And as I told you that actually the polymerization shrinkage is directly proportional to the volume of resin that is entering the addition polymerization reaction. So when the filler volume percentage or weight percentage is increased, the volume of resin that is entering the addition polymerization reaction is actually less. And here we find that the normal polymerization shrinkage of composites is actually between 1% and 4%. Okay. And then the third function is actually reduction in the thermal expansion contraction. So basically, you know that composites are resin-based materials, and resins actually expand and contract to much higher degree when compared to that of the adjacent tooth structure. So the increased filler loading actually decreases the overall coefficient of thermal expansion of the composite. So the change in length per, that is divided by original length, that is in unit time. Okay. So the glass and ceramic fillers thermally expand and contract actually less than do polymers. Okay, the ceramic fillers, that is based on silica, as well as the glass fillers. Okay, the coefficient of thermal expansion is actually less. Okay. Now the overall expansion coefficient actually mainly decreases with filler loading and approaches that of tooth tissue. So when the coefficient of thermal expansion of the restoration and the tooth is actually similar, then we find that there are actually less interfacial stress. Okay. So less interfacial stress is actually produced because of the differential volumetric changes while an individual is consuming hot and cold foods. So when there is intraoral temperature changes, when both the restoration and the tooth are actually having similar coefficient of thermal expansion, then the interfacial stresses at the boundary of the tooth and the restoration will be minimum. Okay. And then, as I told you, the monomer is actually a liquid, and when it is combined with the filler, that is when we are actually getting a paste-like consistency that can be molded to the anatomy of the tooth. Okay, so more filler, more thicker will be the paste. And filler loading, filler size, and the range of filler particle size, shape, all affect the consistency of the composite, and it makes the clinical manipulation, and it enhances the clinical manipulation easier, and it makes it enhances the handling properties. Okay. And then BIS-GMA, as you know, that actually BIS-GMA molecules actually have a tendency to absorb water. There are hydroxyl groups, and water absorption, actually absorbing water actually mainly results, it actually softens the resins and makes it actually more prone to abrasive wear. Okay, so increased filler loading actually decreases the water absorption. And as you know that when you are using heavy metal glasses that is containing ytterbium fluoride or zirconium, etc., or the zirconium, barium, etc., they actually absorb more X-rays. Okay, and they give more radio opacity. Okay, and the final function is actually aesthetics. Okay, now composites are actually used for aesthetic restorations because we find that if they are aesthetic restoration, that means that the refractive index of the restoration and the tooth should actually be similar. And you can see that for BIS-GMA and TEC-TMA, the refractive indices are 1.55 and 1.46. And when they are actually combined, we are actually getting a resultant refractive index of 1.50. Okay. Now, most of the filler particles that are used actually also have the refractive index of 1.50. Okay. So that will actually give it adequate translucency to mimic the tooth structure. Okay. So With that, I'll be concluding my presentation. Thank you.